Alright, this is 2.1 for chapter 2 problems. Area under the curve. So this problem starts off with at t equals 0, an object starts with position xo, or I guess x initial, and velocity v initial, and moves with constant acceleration a. So we have three things. xo, which is, I'll write this here, initial displacement. Then we have VO, which is initial velocity. Okay, and we have A, which is acceleration, but it's constant. This is really important because if it wasn't constant, this would be very hard to solve. So we're given an equation, x of t is equal to xo plus vot plus half at squared. Okay, so it basically asks us to prove this with an v versus t graph. And this is actually really easy because all we need to do is make this graph. Let's say this is time t and this is v. So in order to solve this, we're just trying to get the area underneath the graph, i.e. the integral, right, under the graph, and that gives us the displacement, or the x of the entire thing, x. So that's basically what we're getting the sum of everything. So let's start with VO. So let's just say hypothetically this is VO, right, because VO in every single case won't necessarily always be 0, right, because sometimes you start with a velocity, it's like 3 or something, and then from there you just start on accelerating. So that's our initial. So let me just draw this. And let's say we continue it on for a delta t amount. Alright, so automatically we have this amount of area. Now let's say we're accelerating positively. Because we know our acceleration is constant, that means our line must be linear. That means our velocity for, let's say, for every unit of t, there must be a unit of v. And it's consistent on every single pathway. So the slope is the same on every single linear point on this graph. And so because of that, we have something that looks very analogously similar to a triangle. Look at that. So let's start with this. In order to get this area, we know that's going to be equal to VOT. The next part, the triangle, that's going to be equal to half, right, because it's half of an entire rectangle. It's half times delta t, and I'll just put this in parentheses. And the next one, which is this. And because this is VF, and this is VO, I'm just going to say this is VF minus VO. Now, obviously, if we're trying to prove this, we're not done yet, because this is super weird. So let's just kind of abbreviate that. That's half times delta t times delta v. And so in order to simplify this, because we start at time t0, right? And it's for most problems, right? Time t equals 0, which is basically just when you want the time to start, basically. So we'll just abbreviate this to half times t times, but from this we know v is also equal to vo plus at. Which makes sense because if we have constant acceleration over time, the velocity will increase with respect to time because the acceleration is constant. And so as a result, because our VO is basically negligible because we talked about it earlier, this is basically equal to V equals AT, and so we can just replace this entire delta V, right, with this. So we get something like this, T times AT. So we get half AT squared. And so as a result, we can finally solve this problem. So x of t, we know it has to start with xo, right? Because although it's not geometrically seen in this entire triangle plus rectangle, we know that the displacement starts off with your initial displacement, your xo, all right? And so plus we had this earlier, the VOT, right? It's step 2. This is step 3. Plus the VOT plus the half AT squared. And so we're done.